Thank you for joining this webinar. In this webinar, we'll step a little bit away from the lithium-ion battery and have a look at the supply chain, actually, to make the lithium-ion batteries. I will start with the anode material challenge. Actually, we have really a material challenge, especially in Europe. Talk about silicon manufacturing, especially have a look at silicon refining technologies, because we need a certain quality for battery. And then also, what are the different possibilities for sourcing silicon material for the battery industry? So let's start with the anode materials challenge, but actually before that, there's the live poll. So please fill in. The question is, how much silicon is needed in the lithium-ion battery industry around 2030? Of course, we are in an exponential hockey stick, so it's a little bit a house number. 1 year later, we need much more. But I tried to make a comparison of with the silicon that is used in 2025 in different areas. So you see the photovoltaic solar modules. They today need around 625 kilotons, semiconductor, of course, aluminium industry. And also there's an announcement from Group 14 of 1,000 ton per year plant. So how much plants of this size would we need around 2030 to provide the silicon for lithium-ion batteries? That's something like 10 of these plants. So that are the choices. And I will explain later on, of course, how this looks like. Okay. I see the results, and actually we have a very well-educated auditorium. So this the number 2, the question B is actually the correct one. It will be around 100,000 to 150,000 tons by 2030. What is needed. But let's look a little bit into what's our challenge that we are facing. And this is a graph that comes from 2022, so it's already a little bit older, indicating here on the right side what is the European demand for EV batteries and what is the total demand for lithium-ion batteries in all segments. And then compared to that, you see what is the announced material supply for anode materials, for cathodes. And what you see is there's actually very little anode material supply. So even if we build the gigafactories to provide this sort of material, we don't have the supply chain in place today. And this is a more recent picture from McKinsey in a study they published this year, looking at where the battery materials actually come from. And you see in this violet color the supply from China. And if you look at the anode production of battery-grade graphite, you see that 93%, according to this study, comes from China. Europe has less than 1%. So we are completely dependent on the raw material from material manufacturing in China. Similar LFP and the nickel-containing cathodes, the NMC materials, is slightly more diversified. So we really have a big supply challenge to get the materials that we need for producing the batteries. And let me focus in on silicon, because we have to invest in either graphite or in silicon to get the anode materials. And of course, having not invested yet in the supply chain gives a chance to make decisions for the future. So why silicon? Silicon, of course, is very attractive. It's a second most abundant element in the Earth crust. It's everywhere, so it's not located in an undistributed way. So we can produce silicon wherever you want, more or less. But of course, we have then to look into what are the fabrication lines to make silicon, and how is silicon actually produced. And this is sort of navigational chart. It will appear more often. From top to bottom, the first step is to make metallurgical silicon. That's silicon that has roughly 99.9%. We look into that. That silicon is mainly supplied to silicones and aluminum alloys. That's one of the main outsources, but it's also the starting material to any silicon that has a higher purity than this 99.9%. And we look into the different manufacturing processes during the course of this webinar. But let's start with metallurgical silicon. How does this look like? Metallurgical silicon is typically produced from quartz as a starting material, silicon dioxide, in a submerged arc furnace. These submerged arc furnace, they use an electric current to provide the heat. And the reaction that are going on is you have a reaction at a little bit lower temperature from silicon oxide plus carbon. Carbon is provided as coal, charcoal, and wood to silicon oxide and carbon monoxide. And then there's a higher temperature that through reaction from silicon carbon plus some quartz into the metallic silicon. And you have silicon oxide and carbon oxide as gas is produced. You also see per ton of silicon, you need roughly 30 megawatt hour of electricity, and you need 2.7 tons of quartz, 1.5 ton of coal or charcoal, and 1.5 ton of silicon, of wood to produce that. You see here furnace, typical furnaces that is tapped at the moment. So you get the liquid silicon inside the furnace. Then there's an opening made and the silicon is poured out and crystallizes in these sort of containers that are transported around the furnaces. In Europe, we have big companies doing that, for example, Ferroglobe or Elkem in Scandinavia, but they are all over the world. So this is really a material that is sourced everywhere. Interesting to look, of course, in which areas of the world it is produced. And looking at 2020 on this data, for example, you see again that China has a majority of the production. But in other areas, United States, Canada, Europe, and the rest of the world, there's also silicon production, metallurgical grade silicon production available. When we look where it is used, so the total of the metallurgical grade silicon in 2025, for example, you see a major part is going to the aluminum industry as aluminum alloys. That is relatively constant over the years. So we don't need more aluminum and it's not using more silicon. The second big part is silicones and silanes that are more or less organic molecules based on silicon. For example, think about lubricants, potting materials, sealants. It's also used in the building industry for some components. So this is really a silicon chemistry that is operated. And then on top of that, you see two markets that require highly purity silicon. So they require additional refining steps to make the silicon available. And that's the semiconductor market. And bigger than the semiconductor market, the market for solar modules. So these two markets have a different production process. These two depend on the metallurgical grade silicon, have their own production process to go into chemistry, respectively make an alloy with aluminum. Metallurgical grade silicon, what you need is cheap and abundant electricity because it's electricity heavy, and you want to be close to a source of quartz, either by directly mining the quartz or being near to a port, because at the cost of silicon, the transport costs play a role in the material. So let's have a look at the refining technologies, starting with the oldest one. When we look at very pure silicon, of course, it started with semiconductor silicon. The semiconductor silicon process that is today also widely used in solar starts actually with the metallurgical grade silicon process. You convert that silicon with HCl into a trichlorosilane product. The trichlorosilane product is then condensed and is refined in a distillation step. So it can be evaporated and condensed again. And with every distillation step, of course, it becomes cleaner. So that is used to get to the purity that is needed. And at the end, it is typically reduced into metallic silicon in what they call a Siemens reactor. That's one of the methods where it is a heated rod in combination with hydrogen that leads to the reaction to make metallurgical silicon in a highly pure form that is called polysilicon, and you get the HCl back, which you then can feed into the process again. So this is well established, but what you see, this is a typical picture of such a plant that is done in large chemical plants. These gases are corrosive and explosive, so it's, you have to know the technology to operate that. And that means typically it's done in large investments into big plants. It's not something that can be done on a small scale. More interesting for batteries is, of course, all the routes around the monosilane gas, because that is one of the materials that is widely used to make silicon anodes. And if we look into that, the processes become a little bit more complex. Starting again with metallurgical grade silicon, you make this conversion into trichlorosilane, but then you convert further in different reaction steps till you come to the SEH4, that's the monosilane gas, and some byproduct that is fed into the process again. And again, here it's refining, cleaning, purification of the materials to come to the silane gas. Similar plants from the look at it. So you need a large chemical plant with large investments and also some years of building time and to know how to operate these plants safely. And at the end, silane can be reduced in Siemens reactors or in fluidized bed reactors to get a very pure silicon from the material. But of course, in the battery industry, silane is used in a different way. One of the issues with silane is safety and transport costs. Silane is transported in these sort of containers, but silane is a pyrophoric gas. So it has capable of auto ignition at low temperatures. That means wherever you have a leak of silane, you have a high risk of explosion, and the reaction produces a lot of energy. And you see here some examples of incidents that happened in the past, a silane fire that caused major damage to a plant. In Germany, earlier this year, 2 people actually died because of a silane leak that was detected, and they went in and the silane exploded. So you have to really take care of what you do with the silane. If you transport silane, if your production depends directly on the silane gas. That also makes it costly once you start to transport silane from the silane plant to some other places. In total, trichlorosilane and silane, that is called the silicon purification into polycrystalline silicon. What we have seen is in the past, this technology was widely distributed, talking 2005. We had major players in the US, Germany, Japan, and China. With the rise of the photovoltaic industry in China, that changed. So in 2020, most of the large players, with the exception of Wacker, are actually located in Asia. So that is, let's say, the situation we are in here. Silane, of course, is widely used. I'll come back to that in the also lithium-ion battery, because it's a versatile gas. You can deposit on graphite, on carbon structures, etc. But there's one other method that has been developed for solar in the past, and it's upgraded metallurgical silicon. And that can go up to 5 to 6 nines from the purity point of view, but it is totally different from the chemical reactions that are needed to purify via gas phase. And I want to talk a little bit about that. Again, it starts with the metallurgical silicon process, but the next steps are all based on melting silicon in a liquid form in a container. And purifying, for example, by doing a slag purification. That's a solid material that's generated on top of the liquid silicon that reacts with some of the impurities and confines them in the top layer that can be removed. Vacuum purification, sometimes in combination with a plasma torch, when purities have the tendency to evacuate. This is then a very good method to make the silicon more pure. And the last step is a direction solidification. That's a controlled crystallization from the bottom upwards, which typically drives impurities again in the top layer that can be removed. So these are metallurgical steps that can be used to get silicon clean enough to be used in the battery industry. And the difference, what you have seen with the chemical plants, is these are typically done in these sort of installations. So you have furnaces under argon or under vacuum that are heated by resistance heating, by graphite heaters, for example, and they deal with liquid silicon and crystallization processes. This technology was fully developed for solar silicon, but actually not used for solar silicon, because when the technology was ready on the market, solar has moved into higher purities to get higher cell efficiencies. So the solar was completely dependent on trichlorosilane or silane production. And actually this technology is available, but has never been applied on large scale in solar. The advantage is capex is much lower than for silane gas or trichlorosilane gas plants. It has a much easier permitting and building and commissioning time. These furnaces can be built in series, and you don't need, let's say, permitting of an explosive gas plant that is needed for the other methods. And of course, you can scale in units. So instead of building one large chemical plant with a building time of 3 years and heavy investment, you can actually grow naturally with your market demand by adding these sort of furnaces. So in total, this technology has a lower cost of goods sold from the production point of view. It has a high yield, low byproducts. It's scalable in units and has less capex. So if we can work with that silicon, it has some advantage in providing the supply chain that we need. So when I come back to silicon sourcing for the battery industry, what we see is actually we have two possibilities. It all starts with metallurgical silicon that is produced on very large scale. So compared to the total metallurgical grade silicon production, the amount that we need 2030, 2032 shouldn't be a problem. And otherwise, this technology is all over the world, so the production can be expanded on this part. And then we have a choice. A lot of silicon material produced in the battery use silane as a starting material. As indicated, silane can be relatively cheap when you're close to a silane plant. If you add a lot of transport costs, the price can go up quite dramatically. The scaling of these plants is critical, especially as silane is also used in the photovoltaic and in the semiconductor industry. And they can pay more for the material than the battery. So you have actually 3 industries that are competing on the silane production, which means scaling in large chemical plants is done in large steps, and it's very difficult to forecast these markets on the longer term. Of course, silane is very versatile, so you can use it in silicon carbon composites. You can also use silane to produce nanosilicon powder by direct composition. And also in PECVD coating on copper, there are some companies out there that go to 100% silicon anodes using PECVD deposition of silane gas on the copper foil directly. On the other side, you have this upgraded metallurgical grade silicon. The cost for that is relatively low on large scale, low capex. It can be scaled in a homogeneous way. Products that are out there are micro-sized sheet silicon by a number of players. And this is also the field where we play, because we melt upgraded metallurgical grade silicon again and let it crystallize in this nanoporous silicon structure that is helpful to prevent the silicon swelling. So we think if you're able to tap into this material source, it's easier to scale. It is lower cost at the end. And it can be a good solution for a solid supply chain for the battery industry. That brings me to the end of the webinar. So based on the conclusion that silicon is a viable anode material, I want to summarize silicon is abundantly available, produced worldwide. So when we build a new supply chain, silicon is a very good product, and it can be built up everywhere in the world. The The supply chain challenge lies in the silicon refining because metallurgical grade silicon is not clean enough to be produced to be used in batteries. So you need some sort of higher purity. And then you have two choices. You can go via the monosilane gas. That's a versatile material to be deposited in many forms, but it's capex intensive and it's a relatively high cost. The other route is upgraded metallurgical grade silicon that is low capex, low cost, but then you have to look how to make it usable as battery grade material. One of the big challenges we see and what we're concerned about is where will these investments be made and can the investments be made fast enough? Just to remind you on the question we had in the beginning, we need a silicon supply that's comparable to the semiconductor industry today. But of course, the semiconductor industry had decades to build this production capacity. We are roughly 5 years away from 2030. So it's a big challenge and a big investments into silicon manufacturing capacity if we want to have something comparable. It can be done, but we have to see in which continent and which companies will produce. And the big question is also, do we continue to see China's dominance because of rapid investments into manufacturing, or do Europe and the US pick up the challenge and build their own supply chain? So these are questions that concerns us because we are operating in this field, and it's interesting to see what will happen in the next coming years.